Hello everyone, I welcome you all to this class. This is linear algebra class, and in this class we want to solve this example 3 under this topic we introduced in our previous video, eigenvalues and eigenvectors. In our previous video we saw how we can find the eigenvalues and eigenvectors of a particular square matrix. Now in this example, what is given to us is a linear transformation. So how do we find the eigenvalues and eigenvectors of a linear transformation? Let's see the definition that will help us to do that. So let T be a linear transformation from n-dimensional vector space to n-dimensional vector space. Now we say that the eigenvalues and eigenvectors of this linear transformation T will be the eigenvalues and eigenvectors of any matrix representation of this linear transformation. Now, if you have two matrix representation of a linear transformation, let me say A is a matrix representation of a linear transformation and B is a matrix representation of that same linear transformation with respect to different bases. Then that matrix A and matrix B will have the same characteristic polynomial. In other words, they will have the same characteristic equation, which means that they will have the same eigenvalues. So that's why I say any matrix representation of the linear transformation. So any matrix representation of that linear transformation is okay for us. We'll use this to find the eigenvalues and the eigenvectors. So when we have found it, we have already found the eigenvalues and eigenvectors of the very linear transformation given to you. So in this example, they ask us to find the eigenvalues and the corresponding eigenvectors of the linear transformation mapping R2 to R2. And you know, any vector in this R2 will have two entries, x, y. We have two entries. So V is a vector, is arbitrary vector, which has entry x, y in this R2. And the transformation of any of this arbitrary vector is given by this formula. So we are going in this example we use what? The standard basis. So when we use the standard basis to find the matrix representation. So when we do that, we will now get the eigenvalues and eigenvectors of that matrix representation. So let's start. Solution. So what we are going to do is we'll start by saying let V1, I want V1 to be a particular standard base of this R2. So you know the standard basis of R2. The first one will be have an entry 1, 0. Second one will have entry 0, 1. So these are the two standard bases. So we'll have two standard bases for R2. So let V1 be the first standard base. We'll have entries 1, 0. This and V2, let it be the second standard base, which will have entry 0, 1. So let V1 and V2 be the standard basis of what? R2. Then the transformation of V1. Transformation of what is your V1? V1 has entry 1, 0. So let's transform it. The first entry is what? Is your x. Your x is the first entry. So what is our first entry here? Is 1. So you have to multiply it by 2. So 2 multiplied by 1 is what? 2 plus. We have plus 4y, right? What is your y? Y is the second entry. What is the second entry here? 0. So 4 multiplied by 0 is 0. So if you add, you get what? 2 plus 0 is 2. Right? So 2 will be the first entry of the transform vector, comma. We have comma here, right? Then to get the second entry is saying x minus y. What is your x? The first entry of the vector you are transforming. What is the first entry? 1 minus y is the second entry of the vector you are transforming. What is the second entry? 0. 1 minus 0 is what? 1. V2 will be transformation of what is your V2? V2 has entry 0, 1. So 0 is the first entry, which is your x, according to this formula. So your formula say 2 multiplied by the first entry. 2 multiplied by 0 is 0 plus 4 multiplied by the second entry. Second entry here is what? 1. Is what? 4. Right? So if you add 0 plus 4 is 4. So we have gotten the first entry of the transformed vector. Then the second entry will be x minus y. What is your x? The first entry of this vector you are transforming. What is the first entry? 0. Minus y is the second entry. What is the second entry here? 1. 0 minus 1 will have negative 1, right? So this is what we got. So let's write down the metric representation. Now the metric representation will be since the vector we got, they are they are row vector, right? So we are going to write them as what? Column vector. So each of them we write it as column vector. That is, we transpose it. Then when we transpose it, they will form the columns of this matrix A. So if you transpose this first one, how will it look? It will look like this: 2, 1. If you transpose it, so it will form the first column of this matrix: 2, 1. If you transpose the second one, how will it look? 4, negative 1. So the second column of this metric representation will have entry 4, negative 1. So this is basically what we have. So this is the metric representation of this linear transformation with respect to the standard basis. You need to solve this equation. We call it the characteristic equation. Determinant of a minus lambda I and equate it to 0. We saw this in our previous video. This is the characteristic equation you use to find the eigenvalues of any square matrix. You can see the metric representation of the linear transformation in a square matrix. We do the same thing, right? So this implies determinant of, you write down your matrix A minus lambda is a scalar and I is your identity matrix. The identity matrix will be 2 by 2 because your matrix A is 2 by 2. I have 2 by 2 identity matrix. Determinant equated to 0. So this implies, so the first thing we have is our matrix A minus, we can use lambda to multiply identity matrix. Lambda multiplied by 1 is lambda, lambda multiplied by 0 is 0, lambda multiplied by 0 is 0, lambda multiplied by 1 is lambda. Then we have determinant equated to 0. So we can subtract the two matrices, right? 2 minus lambda, I have 2 minus lambda, 4 minus 0 is 4, 1 minus 0 is 1, and negative 1 minus lambda, I have negative 1 minus lambda. Determinant equated to 0. So we have 2 by 2 matrix. We want to find the determinant of it. So what you do, you multiply the entries of the principal diagonal. That's 2 minus lambda multiplying negative 1 minus lambda. Then you subtract the product of the other diagonal. That's 4 multiplied by 1 is 4. Then equated to 0. Then next thing, you expand, right? 2 multiplied by negative 1 is negative 2. 2 multiplied by negative lambda, negative 2 lambda. Negative lambda multiplied by negative 1 is positive lambda. Negative lambda multiplied by negative lambda is positive lambda squared. Then we have minus 4 equated to 0. So let's continue the solving this side. We can write the lambda with the highest power first, right? That's, we write positive lambda squared. Then negative 2 lambda plus lambda will give you negative lambda. Then negative 2, negative 4 is negative 6. And equated to 0. We have a quadratic equation. We can factorize, right? So what's the coefficients of lambda with the highest power? That's coefficients of lambda with power 2 is 1. Use the coefficient to multiply the constant term. The constant term is negative 6. So what 1 multiplied by negative 6 is, will give you negative 6. Look for the two factors of negative 6 such that the product will give you negative 6 and the sum will give you the coefficient of the middle term. The coefficient of the middle term is this term with lambda. So what's the coefficient? Negative 1. So let's get the two factors. The two factors will be -3 and +2. 2 multiplied by -3 is -6, and if you do 2, if you add 2 and -3, you are going to get -1. So the first lambda will have coefficient of +2, and the second lambda will have coefficient of -3, right? So this will give us is equivalent to the middle term. 2 lambda minus 3 lambda will give us negative lambda. So this implies lambda squared plus 2 lambda minus 3 lambda minus 6 equated to 0. So this simply implies we can factorize. Lambda is common here. Lambda into lambda plus 2, right? Then the common factor here is -3. -3 into, if you use -3 to divide -3 lambda, you have lambda. -3 divided by -6, you have a +2 equated to 0. So we can pick the coefficient of this bracket, lambda minus 3. So I'm picking what is here and what is here, right? Then form the first bracket. Then pick any of these brackets since they are the same. Lambda plus 2 equated to 0. So the next thing we are going to do is to find the values. So the product of these two quantities are giving us 0. It means that lambda minus 3 is 0, or this lambda plus 2 is 0. These are the two possibilities for the products to give us 0. This implies if you move -3 to the right, you have lambda will be +3, or if you move +2 to the right, you have that lambda will be equal to -2. So these are the eigenvalues. So from what we got here, the eigenvalues are what? 3 and -2. The 3 and -2 is also the what? They are the eigenvalues of the linear transformation as well. So with this we have gotten the eigenvalues of the linear transformation as well. So next one is to get the corresponding eigenvector. So for us to find the corresponding eigenvectors, we'll solve this equation. We will solve this equation. A minus lambda I multiplied by capital X equated to 0. So this is the equation we are going to solve. As we saw in our previous video, we use this equation, right? So our A is the matrix we have, right? This was the metric representation of the linear transformation we got, remember, right? Then minus lambda is a scalar, then your I, the identity matrix, which has entry 1 0 0 1, right? Multiplied by capital X is the eigenvector you are looking for. It have entry x1 x2 equated to the 0 vector, the 0 matrix. So 0 is the 0 matrix, right? This capital X is the eigenvector you are looking for. It will have entry x1 and x2. It will be a column vector. So, and it will have entry x1 and x2 because your matrix A is what? 2 by 2. If your matrix A is 3 by 3, it will have entry x1, x2, x3. This is what we have, but we are going to solve for the first lambda. For lambda equals, the first lambda is what? 3, right? We have, so we are going to solve for lambda equals 3. We are going to have, so our lambda now is now 3. So we are going to have -3 multiplied by the identity matrix, right? Multiplying the column vector equated to the 0 matrix. then this implies, so let's use the 3 to multiply identity matrix, right? 3 multiplied by 1 is 3, 3 multiplied by 0 is 0, 3 multiplied by 0 is 0, 3 multiplied by 1 is 3. Then multiplied by the column vector equated to the 0 matrix. So this simply implies we can subtract, right? We can subtract the two matrices. 2 minus 3 is a negative 1, and 4 minus 0 is 4. 1 minus 0 is 1, and negative 1 minus 3 is negative 4. Multiplying the column vector equated to the 0 matrix. So this is what we got. So the next thing is to see how we can solve this equation. Before we solve it, we need to reduce this matrix, right? We need to reduce this matrix before we solve this equation, so that we can, solving the equation is just getting these entries x1 and x2. So but we need to reduce this matrix first using a roll operation. Now let's write down the matrix and reduce it. So in the reduction process, I will make the first entry of a row, first non-zero number in a row, which we call the leading entry of that row. I will make it to be positive 1, so that our equation will be easier to solve. So what's the first entry? The first non-zero number in this first row is this negative 1. So I will make it positive 1. So I know that if I multiply this negative 1 by negative 1, it will be positive 1. So I'll have row 1 multiplied by negative 1. So I'll do that. Let's carry the operation. Negative 1 multiplied by negative 1, positive 1. Positive 4 multiplied by negative 1 is negative 4. So I've done that. Then, since after that first non-zero number in that row, you know the first non-zero number in this row 1 is located at what? Column 1. Is located at column 1. So we are going to make the entries below that number to be 0 in that column. So what is below this negative 1 in column 1 is what? This positive 1. We'll make it to be 0. How do we make this positive 1 to be 0? Negative 1 plus positive 1 will give us 0. So simply since this first entry is negative 1, if you add it to this positive 1, it will be 0. Simply we are going to add row 1 and row 2 together. So because of that, I'm going to multiply row 1 by positive 1. Why am I multiplying it by positive 1? Because I don't want it to change. I want it to be the same thing, so that I can add it to row 2. So I will do that. I will do row 1. This thing I wrote is row 1 multiplied by positive 1. I'm using positive 1 to multiply row 1. And I'm adding result to what? Row 2. That's the meaning of this thing I wrote. So let's do that. You know, if you use positive 1 to multiply row 1, it will be the same thing. And that's the reason why I'm doing that, so that it will be the same thing. I'll add it directly to row 2. So negative 1 plus positive 1 is 0. Positive 4 plus negative 4 is 0. So with this, we have reduced this matrix. So we have, what we are going to have now is, we are going to replace this matrix with the reduced form. So let's replace it in this equation. And when we have done that, we can easily solve the equation now. So let's do that. So after doing it, we have replaced it. After doing that, the next thing we are going to do is to check whether each column of this reduced matrix, whether each column has a leading entry of a row. Leading entry of a row is the first non-zero number in a row. So what is the first non-zero number in this row? In row 1 of this reduced matrix, the first non-zero number is positive 1, which is the leading entry, right? So, and this positive 1 is located at what? Column 1. So column 1 has a leading entry of row 1. Now column 2, there are zeros throughout, no non-zero number, so no leading entry. So this makes column 2 not to have a leading entry of any row. So column 2 does not have a leading entry of a row. Now x1 is corresponding to column 1 and x2 is corresponding to what? Column 2. So since x1 is corresponding to column 1 and column 1 has a leading entry of row 1, so column 1 will not be a free variable. X2 is corresponding to column 2. Column 2 does not have a leading entry of any row, so x2 will be a free variable. So we are going to call it a particular constant. We can call it alpha. So you say let x2 be equal to alpha. This alpha will be a real number, right? Because the entries of your metric representation, they are real, right? So alpha will be a real number, and we are going to call it a free variable. So this is what we have. So once you have done that, you can now do the multiplication and solve the equation. To do that, start from the last row. X1 multiplied by 0 is 0, x2 multiplied by 0 is 0. 0 plus 0 is what? 0, equated to 0. So basically, we did not get any value for x1 and x2, right? So we'll go to row 1. x1 multiplied by 1 is x1, and x2 multiplied by negative 4 is negative 4x2, equated to what? 0. Equated to 0. So if you make x1 a subject of the formula, you have what? X1 will be equal to, if you are going to move negative 4x2 to the right, you have positive 4x2. But what is your x2? Your x2, we have called it alpha. So we have positive 4 alpha, right? So with this, we have gotten the values of the x1 and x2. So our column vector having entry x1 and x2 will be equal to, your x1 is 4 alpha and your x2 is alpha. So alpha is just a real number. We are going to choose one alpha. So somebody can choose alpha to be 2, 3, 4, 5, and so on. But we will choose the simplest alpha. We'll choose 1. So let's choose 1. So 4 multiplied by 1 is 4, and here will be 1. So we have gotten this eigenvector corresponding to lambda equals 3. So we have gotten it at alpha equals what? At alpha equals 1. So at alpha equals 1. So this is what we got. So we are going to solve for the second lambda. For lambda equals negative 2, right? That was the second lambda. We can go ahead and do the substitution. What is your matrix A? So write down the matrix A. This was our matrix A, right? Then this was the matrix A we got. Then we are going to have lambda 2. Lambda 2 is negative 2. So we are going to do negative negative, which will be positive. 2 multiplied by the identity matrix I. So we have the identity matrix. So this is our identity matrix. Then your x is the column vector, then equated to the 0 matrix. So this is what we have. Let's complete the solving here. Let's write down our matrix A. Then plus, we use 2 to multiply identity matrix. 2 multiplied by 1 is 2. 2 multiplied by 0 is 0. 2 multiplied by 0 is 0. 2 multiplied by 1 is 2. Then multiplied by the column vector equated to the 0 matrix. So this is what we have. We can add 2 plus 2 is 4. 4 plus 0 is 4. 1 plus 0 is 1. Negative 1 plus positive 2 is positive 1. So with this we have added, multiplied by this column vector equated to the 0 matrix. So this is basically what we have. As we did earlier, to solve this equation, that's to find the entries x1 and x2, we are going to first of all reduce this matrix. We are going to reduce it using row operation, right? As I said earlier, when we are doing the reduction of the other one, I say I will make the first non-zero number in each in this that's the first non-zero number in a particular row. If we have such, I will make it to be what? 1, positive 1. So if you come to row 1, the first non-zero number there is 4. So I want to make it to be positive 1. How do I make it to be positive 1? Multiply it by what? The reciprocal of 4. What's the reciprocal of 4? 1/4, right? So I'll have row 1 multiplied by 1/4, right? So let's do that. If you multiply row 1 by 1/4, you are going to have 1, 1. So then we are going to make that 4 is located at what? Column 1, and what is below it in that column is 1. We are going to make that what is below it to be 0. So how do we make this positive 1 to be 0? I know that negative 1 plus positive 1 will give us 0. So what I will do is that I will make this positive 4 to be negative 1, so that I can add it to this positive 1, so that it will be 0. How do I do that? I will multiply this negative 4 by negative 1/4. So I will multiply it by the negative of the reciprocal of what? 4, and add it. So let's do that. So row 1 multiplied by negative 1 divided by 4, right? Row 1, I'm multiplying this thing I wrote, I'm multiplying row 1 by negative 1 divided by 4, and I'm adding the result to what? Row 2. So let's do that. Negative 1/4 multiplied by 4 will give you negative 1. Negative 1 plus positive 1 will give you 0. Negative 1/4 multiplied by positive 4 will give you negative 1, plus positive 1 will give you 0. So with this one, I will reduce this matrix, right? So we have, what we are going to have now is, we are going to replace this former matrix with the reduced form, right? So let's replace it. This is the reduced form. I've replaced the former matrix with the reduced form. So once I've done that, the next thing is to check whether each column has a leading entry of a row. The leading entry of row 1, which is the first non-zero number in row 1, is this positive 1. It's located at column 1, and which means that column 1 has a leading entry of row 1. Row 2, there are zeros throughout, so this makes column 2 not to have a leading entry of any row at all. So column 2 does not have a leading entry of any row. So, and from what I said earlier, x1 is for column 1 and x2 is for column 2. Since column 1 has a leading entry of a particular row, which is row 1, x1 will not be a free variable. Column 2 does not have a leading entry of any row, so x2 will be a free variable. We are going to say let x2 be equal to alpha, element of free numbers. We say is what? Free variable. So once we have done this, we can solve. Start from the last row and multiply. X1 multiplied by 0 is 0. X2 multiplied by 0 is 0. 0 plus 0 is what? 0. That's 0 equal to 0. Do we get any value for x1 and x2? The answer is no. So we go to row 1. X1 multiplied by 1 is x1 plus x2 multiplied by 1 is x2, equated to what? 0. So x1 plus x2 equals what? 0. This implies that x1, if you make x1 is also the formula, move positive x2, right? So x1 will be equal to negative x2, because if you move positive x2 to the right, it changes to negative, right? Negative x2. So this will be equal to, what is your x2? x2 is alpha, so x1 will be equal to negative alpha. So with this, we have gotten your x1 and x2. So our column vector having entry x1, x2 will be equal to, so your x1 is negative alpha, your x2 is what? Alpha, right? So this will be equal to, we are going to choose a particular value for alpha, because alpha is any real number. So any real number you choose will give you an eigenvector for that lambda equals negative 2. So we are going to choose, let's choose a particular lambda. Let lambda be 1. So if you choose lambda to be 1, we are going to have what? negative 1, because we have negative alpha here, negative 1, we are going to have 1. Then at alpha equals what? 1. So we have gotten the eigenvector corresponding to this very lambda. So the first eigenvector we got, remember the first eigenvector we got was this at alpha equals 1, and then the second one you have it here at alpha equals what? 1. So these are the eigenvectors we got when we choose alpha to 1. So these are the eigenvectors we got at alpha equals 1. So thank you so much for being part of this class. See you in the next class.